This is a solutions video where I'm walking through Unit 4 practice test that was given to my students in 2022 to 2023 school year, which we use in the 2023-2024. Unit 4 is all subjects related to work energy. I've already sketched all the sketches and done all the work, so I'm going to talk through it. I'm going to do so in a quick fashion, otherwise this video would be very long. Number one, how much work would a child do when pushing a 12-kilogram wagon, distance of 2.7 meters with 22 Newton horizontal force? Important words. We're going to push with a wagon that has a mass of 12 kilograms, a distance of 2.7 meters, with a force of 22 newtons. And the other word that's really important is horizontal force. I've drawn it probably incorrectly. I look like I'm pulling it. Oh, I am pulling it in the words up here, pulling it. But the most important thing is that the force is horizontal. There's no angle to it. So there's a free body diagram acting on the wagon, and the displacement's to the right, the force is to the right, and the angle between the displacement vector and the force vector are 0. If you put those on top of one another, the angle is 0. Now I can use the equation for work equals force times distance times cosine of theta. Theta is 0, cosine of theta is 1. So 22 times 2.7 is 59.4 joules. This is done from a test generator. The test generator will examine and give answers with correct sig figs. So if you'll notice 12 is 2, 2.7 is 2, 22 is 2. My answer has to have 2 sig figs. So that's where that came from. Your exams are not multiple choice, so I just tell my students in physics to give me three sig figs and you should be good to go. You don't get graded on sig figs, which is crazy. That's an AP exam style grading. All right, number 2, child does 350 joules of work while pulling a box from the ground up to his treehouse at a steady speed. In other words, constant speed with a light rope. In other words, we don't worry about the mass of the rope. The treehouse is 8.4 meters above the ground. What's the mass of the box? Here's all the pieces of information that was given. Work is 350 joules. We're going to pull at a steady speed. What does that mean? Acceleration 0. Velocity is constant. The treehouse is 8.4 meters above the ground. That's how far we're pulling it. So we're going to do that displacement in the work equation is 8.4 meters. If I drew a free body diagram on the box, technically the rope is putting a force upward, force of tension. The force of gravity is acting downward. The acceleration is 0 because they said steady speed. And therefore, the force of tension, which is what the child is doing, the child is putting that tension in that rope, is equal to the force of gravity. So those two forces have to be equal to one another. If I wanted to find the distance, I'm sorry, what do they ask for? What's the mass of the box? I'm going to use the relationship of work equals force distance cosine theta. Work is being done by the child. What is the equation? What force is the child putting on F of child, which is, by the way, the tension, which we have stated is equal to force of gravity, which is mg. And so that's why I've replaced that with mg. The distance was given, cosine of theta. If you look at the displacement vector and the force of tension, what the child is doing, they're on top of one another at 0 degrees. And I can rearrange that equation for mass. Since I knew how much work was being done because they gave it to me. So I know work, I know distance, I know g, and I know cosine of 0 is 1. And I can solve that equation for mass and plug in the values that were given. 4.25 kilograms is what I got. 4.3 is to 2 sig figs, because that's the number of sig figs, the maximum number of sig figs. I'm sorry, the minimum number of sig figs. By the way, 350 is 2 sig figs, just so you know, that we don't count trailing zeros unless they're after a decimal. Number 3, a 60 Newton, that's the weight of the box, which is equal to Fg, which is equal to mg. A 60 Newton box is pulled upwards 4 meters. along a surface of a ramp that rises 37 degrees above the horizontal. How much work does gravity do? So every force has the potential to do work, and they're asking about how much work does gravity do. So I have to the left a sketch of this box being pulled up a surface by some force applied. They told me that the incline of that box was 37 degrees. Now off to the right, I have a free body diagram of the force applied up the ramp, force normal, which is perpendicular to the ramp, force of gravity, which is straight down towards the earth. The work is being done. They want to know how much work of gravity, force of gravity is doing. So equation for work equals force, distance, cosine theta. Well, what work are we interested in? We're interested in the work being done by force of gravity. So I've replaced the force in that equation with force of gravity. Distance cosine theta. Now I've got to evaluate what the angle is. So let's go back over here to this free body diagram. I need the angle between the displacement and force of gravity. They told me that that angle of that incline was 37 degrees. They told me the force applied was horizontal to that incline. So that means the force applied is 37 degrees above the horizontal. In addition, force of gravity is straight down, which is 90 degrees to the horizontal. So if I want to know the angle between the force vector, force of gravity, the one we're interested in, and the displacement, I have to add 37 to 90. So theta is 127 degrees in this particular situation. So that's why cosine of 127 is been written. I apply that and calculate it. By the way, cosine of 127 is a negative number. That means the work done by force of gravity in this situation is negative. Negative 144.4 joules, 2 sig figs gives me 140 joules. That's why it's the letter B. Again, I'm not judging on correct sig figs. Number 4, because force of gravity is a conservative force, and they want to know how much work force of gravity did. All I really care about is the final and initial location. A conservative force doesn't matter about the path that it took. It only deals with the final and initial. So the work equals force times distance times cosine theta. The force of gravity acting on the pebble is this equal to the weight of the pebble, which was given as 2 newtons, times the distance that force of gravity was acting on it, and the distance can be calculated by 16.5 minus 1.5 times cosine of the angle between the force of gravity and the displacement. Force of gravity is downward, displacement is upward, so the cosine of 180 is used. That would be, once you plug that into your calculator, you would get work is equal to 30 joules, and that is the letter, it's negative 30, by the way, because cosine 180 is negative 1. And notice they did give you the wrong answer of positive 30. So you would have gotten that wrong if you did not pay attention to the direction of the displacement between the initial and final location, and the fact that force of gravity is going in the opposite direction. Number 5, how much kinetic energy does a 0.3 kilogram stone have if it's thrown at 33 meters per second? The kinetic energy equation is 1/2 mv squared. We have all the values. It is a plug and chug. Everything is in the correct unit. So a half times 0.3 times 33 squared, 163.35. 2 sig figs. We have to get rid of this is 160 joules. That's just 2 sig figs. So the answer is D. Number 6, how much work must be done by frictional forces to slow a 1,000 kilogram car from an initial velocity of 29.4 meters per second to a final velocity of 0? So that information was provided. We know that energy initial plus work equals for energy final. It is not conserved. Energy is not conserved. Energy initial, this is a flat surface. There's no height, there's no spring, so the only energies are kinetic that we're interested in. And that, by the way, is the work energy theorem, which applies to an object that's not a part of a system. So at any rate, kinetic energy initial plus work is equal to kinetic energy final. Rearrange it for work equals change in kinetic energy. I have everything I need to solve it. 1/2 mass v final squared minus 1/2 mass v initial squared. The initial velocity is 0, so the I'm sorry, the final velocity is 0. So that cancels, that term is no longer needed. And so I really only need to know the initial kinetic energy to determine the amount of work that was done by frictional forces to bring that car to a stop. And that becomes 4.32 times 10 to the 5th. And that is to 3 sig figs. And that is letter B. When a car of mass of 1390 kilogram accelerates from 10 meters per second to some speed that we don't know, 4 times 10 to the 5th joules of work is done. Find the final speed. And again, this is the work energy theorem, which is applicable to an object that's not a part of an Earth object system or a Earth object spring system. So the only thing that work is going towards is the change in kinetic energy. So if I expand the work energy theorem, and I know that the change in kinetic energy is the kinetic energy final minus the kinetic energy initial. And then I will expand that further since, again, I have both a final and initial. I can't cancel anything out, and they're asking for, oh, they told me work, excuse me. So I've expanded it, and then I'm going to multiply times 2 to get rid of the halves. So I get 2 times the work is equal to mass times final velocity squared minus mass times initial velocity squared. I'm going to solve for the final velocity. So I have to add mv initial squared to both sides and then divide by mass, take the square root, and that will equal the final velocity. Be careful with your calculator. Please try to learn how to use the double E for scientific notation in your calculator. If you do it correctly, you should get 25.99 meters per second. And with 2 sig figs, that's 26. Actually, to 3 sig figs, that's 26.0 meters per second. Notice all of the values were given to 3 sig figs. Number 8. A 1,000 kilogram car experiences a net force of 2,500 newtons. That's the net force acting on the car while slowing down from 30 meters per second to 22.4 meters per second. How far does it travel? So here's a picture of the car, goes some distance, it changes velocity between the final and initial. If you think about the forces acting on the car, it has to have a net force acting to the left. If it's traveling to the right because it's slowing down, that angle between those between the force, the net force, which is what we care about, and the displacement vector is 180 degrees. The total work done is equal to its change in kinetic energy because I don't have any potential energy due to gravity because I'm not changing heights and I don't have a spring. So once again, this is a work energy theorem application only to an object. We know the definition of work is FD cosine theta. They asked for the distance. So I've got to expand the work and I need to expand kinetic energy final and initial. By the way, they don't cancel because I have a final and an initial velocity. So I've changed work to be force net times d times -1. Where did -1 come from? -1 came from the fact that cosine 180 is -1. Then I have 1/2 mv final, and that is the kinetic energy final, and then minus the initial kinetic energy, 1/2 mv initial final. So I can't delete any terms, but I can get rid of the halves by multiplying through by 2 everywhere. And then I can rearrange that equation for D. So I did that over here. D is equal to the difference between the mass times final velocity squared and the mass times initial velocity squared. Now I factored out the mass just so I could make my calculations easier. You don't have to do that, but I did. And then if I were to plug that into my calculator correctly, I would get 20.96 in the units of distance as meters, and I used all the correct units. 20.9 to 2 sig figs is 21 meters. Number 9, it takes 96 joules of work to stretch a spring from 1.4 to 2.9 meters from equilibrium. Okay, so I have gone from 1.4 meters from x equals 0 to 2.9 meters from x equals 0. That's what this term equilibrium means. and they want to know the value of the spring constant. What was given to me in the equation, or the other piece of information that I had to know is how much work was done. So I have a sketch here. I have x equals 0. That's the natural length of the spring. But I didn't start there. I actually started here at 1.4 meters, and then I will call it the final location. Now, we started at rest, somebody put a force on it, and now I'm hanging out there at x equals 2.9, and the amount of work was 96 joules. So the change in energy is equal to work. There is somebody doing work on the spring. Somebody's pulling on the spring with the force applied to get it there, okay? And so we're only interested in potential energy due to a spring because I have no initial velocity, I have no final velocity, I have no change in height. So the initial energy plus work equals final energy. You can see that all the terms cancel except for the initial spring's energy and the final spring energy. And then, of course, the work. They wanted the work. So I did that a long way. I didn't have to, but I did that to help you see that if you continue and you rearrange, you'll get the work is equal to the final minus the initial, which is this equation, delta E equals work. And that's what I have always said is one of the most important energy relationships. The change in energy is equal to the work done on the object or the system of object. It applies to many different things. And that's actually what we did. So the amount of work, which we know because it was told, is equal to 1/2 k x final squared minus 1/2 k x initial squared. I'm going to multiply through by a 2. I'm not sure where that half went. To get rid of my halves, I'm going to factor out the k because, again, I'm trying to find k, and I got to get k by itself. So that's where this comes in. And now I can divide both sides by the polynomial x final squared minus x initial squared, and then I can solve using algebra. Please be careful when you enter this into your calculator. Make sure you use parentheses on the denominator, especially unless you work and find individual values and go that route. But at any rate, it's 29.76 newtons per meter, and that to 1 sig fig, actually. Yeah, and to me, they're not consistent. They give this in only 1 sig figs, but at any rate, it's 29.76. I would not give you answers like that. You would have to show your works and circle your answer. Number 10, another spring problem. An ideal spring with a spring constant of 20 newtons per meter is stretched from its equilibrium point, that means x equals 0, to 2.9. How much work is done? Again, work is equal to change in energy. So the only energies that I care about in this problem, because I'm going to start at a certain velocity of 0, I'm going to pull with my finger. I'm putting a force on it. So there is an outside force. My hand is pulling on that spring. And I'm going to stretch that spring to x equals 2.9. They told me the spring constant. They told me the x initial location was 0 and the final was 2.9. Again, energy initial plus work equals energy final. Because I don't have a velocity or a change in height, it is basically the potential energy due to the spring plus work equals potential energy due to the spring final. The only thing that has, again, the initial potential energy due to a spring is 0 because x is equal to 0. Everything else cancels except for the potential energy due to a spring final. So the amount of work is equal to the energy stored in the spring and its final location. All the values were given, 84.1 joules, which is letter A. Here we go. Number 11. A block slides down a frictionless incline ramp and experiences no air resistance if the ramp is 44 degrees above the horizontal and the length of the surface of the ramp is 28 meters. Find the speed of the block as it reaches the bottom of the ramp, assuming it started from rest. So here's my picture. The box is at the top. They told me it was frictionless, so I have smooth written there. It travels down the ramp the distance of 28 meters, which they told me. They told me the angle of incline was 44 degrees above the surface of the horizontal, excuse me. Want to know the final velocity after that distance. I assume that's at the bottom of the hill, but doesn't matter. It would still be that same location. Initial, I say, is at the top, final is at the bottom. This is, again, there's no outside friction, there's no external forces, so the change in energy is equal to 0. In other words, energy initial has to equal energy final, which is located right here. And so the only energies I have are energy due to gravity, kinetic energy. And so potential energy due to gravity initial, kinetic energy initial has to equal potential energy due to gravity final, and kinetic energy final. Because I have potential energy due to gravity, I must select my 0 line, and I need the height above my 0 line at the initial location, which they did not give me, but they gave me enough information to take over here and draw a triangle that is a right triangle, and then use SOHCAHTOA. So since I have 44 degrees, the height is the opposite from that, and I have the hypotenuse. The sine of that angle is equal to the opposite side, which is the height I'm interested in, divided by the hypotenuse. So the height is equal to 28 times sine of 44. Your degrees, your calculator must be in degree mode. That's 19.4 meters. Now going back to my energy equation, the only energy initial is potential energy due to gravity, and the only energy final is its kinetic energy. Mass cancels. I'm trying to find the final velocity. So I multiply by 2 and divide by, and then take the square root, excuse me. And then so 2 times 9.8, that's g on the surface of the Earth. And then divide by multiply times the height, which we calculated using SOHCAHTOA, and take the square root of that product. And you'll find that the height is equal to 19.49 meters, which is 19.5 to 3 sig figs. Number 12, a prankster drops a water balloon from the top of a building. If the balloon is traveling at 29.1 meters per second, when it strikes a window ledge that is 1.5 meters above the ground, how tall is the building? So I have a sketch over here to the left. I have a person on top of a building with a water balloon that they have dropped. Since they dropped it, it starts with the velocity of 0. Some location later, which they told us the location, which is 1.5 meters above the ground, its velocity is 29.1 meters per second. There's no friction and no outside force of the balloon Earth system, so energy initial must equal energy final. Energy initial can be expanded to kinetic energy and potential energy due to gravity because I have a height change. I don't have a spring, so I can ignore the spring. Again, that energy initial must equal energy final, and I wrote out all four, both kinetic energy and potential energy in both locations. And then I go through each one and determine if any of them are 0. The kinetic energy initial is 0 because the initial velocity is 0. The potential energy due to gravity initial is not 0 because it is something above the 0 line, which, by the way, I have selected the ground as my 0 line, is equal to the final kinetic energy, which is a value because I have the velocity at the final location, and I have to add the final potential energy due to gravity, which is also not 0 because they told me that ledge was 1.5 meters above the ground, which is the location of the 0 line. I can cancel all masses and I can multiply everything by 2 to get rid of my fractions. Mass was brought to the party by everyone. So I will get an equation that states that the twice times g times height initial equals final velocity squared plus 2gh final. They asked for the initial height of the building, so I'm looking for h initial. I will rearrange that equation using algebra, plugging in my values, paying close attention not to forget my square, and also making sure I use my calculator properly. I will get the height of the building to be 44.7 meters, which is 45 to 2 sig figs, and the answer therefore is A. Number 13, a 60-kilogram skier pushes off the top of a frictionless hill with an initial speed of 4 meters per second. How fast will she be moving after dropping 10 meters in elevation? We can assume air resistance is negligible, and since they didn't tell us there's friction on the snow, we assume there's no friction. Therefore, energy is conserved. Energy initial has to equal energy final. We were told the mass of the skier, although I don't need it. We were told the initial speed of the skier. We were told the height in elevation. So that is not the distance of down the ramp, it's the elevation. So it was 10 meters. The only two energies I care about are kinetic energy, potential energy due to gravity. There's no spring. I've expanded the initial energy to equal the final energy. And then I go through each term and ask myself, is anything zero? Initial kinetic energy is not zero. I have velocity. Initial potential energy is not zero. I have height. Final kinetic energy is not zero because there's a speed there. I did not locate my zero line, but there you go. The final potential energy due to gravity is zero because the height above the zero line is zero. So multiply everything by 2. Everybody brought mass to the party, so I can cancel mass. And then the equation becomes a little more simple to solve. The question asks for its final speed at the bottom, so I will solve for V final, and all the other values are known, and I will find that the final velocity at the bottom of the hill was 14.5 meters per second. The next two, in my opinion, I've used as extra credit problems, but I like it to give students challenging problems. So number 14 is a 5 Newton, that's the weight, which equals mg. Projectile leaves the ground with a kinetic energy, so it tells me the initial kinetic energy of the object and its weight. At the highest point in its trajectory, we have a kinetic energy of 120 joules. And they ask to know what is the vertical height at that location relative to its launch. We have no air resistance, we have no outside force, therefore energy initial must equal energy final. Therefore, I have broken up the energy initial and energy final into the sum of the kinetic energy, potential energy due to gravities at each location. I have ignored potential energy due to a spring because we have no spring in this problem. We were told the initial kinetic energy. We have no potential energy initial because the zero line is at the bottom, which is where it started. We were told the kinetic energy final of 120 joules at the top. And then we have mgh final as its potential energy due to gravity final. We were asked its final height. We can solve that equation for h final. And then we realized we were not told the mass. In order to find the mass, I must use the fact that the weight was given. The weight of 5 newtons was given. Weight is equal to force of gravity, which equals mg. Assuming I'm on Earth, so I take and rearrange that equation for mass and say 5 newtons divided by 9.8 gives me 0.51 kilograms. And now I can use that 0.51 kilograms in my equation and solve for the final height, which is 20 meters. A little bit of critical thinking there. Next problem, I have a 1,500 kilogram car moving at 25 meters per second. It hits an initial uncompressed horizontal spring with a spring constant of 2.0 times 10 to the 6 Newton per meter. What's the maximum displacement of the spring that it compresses? Well, at maximum if you can imagine something hitting a spring, and at the maximum displacement, the object comes to a halt before it starts to go backwards. So we know the final velocity is 0 at the maximum displacement. I've listed here all of the values that were given to us. We know that the k constant, we know the mass, we know the initial velocity, and we know that at the max distance or displacement of the spring, the velocity is 0. If we assume that the system is defined as the car and the spring system, don't really have to include Earth because Earth, we have no change in height. So we really only are interested in potential energy due to a spring and kinetic. Energy initial has to equal energy final. I've expanded those initial and final energies to the energies that are involved in this problem. Spring initial kinetic energy initial, spring final kinetic energy final. Those have to be added up and the total equals each other at its initial and final locations, which I've labeled on my graph. I'm going to go through each term. I know that initially the spring is not compressed because the car hasn't hit it yet. And so the potential energy due to spring initial is 0. It has a kinetic energy initial because it has a velocity. It has a potential energy due to a spring final because we've compressed the spring, which brought the car to a stop. It has no kinetic energy final because the velocity is 0 at its max spring displacement. By expanding then the kinetic energy initial to 1/2 mv initial squared, and the potential energy due to a spring final, which is 1/2 kx final squared, and solve for what they've asked, which is the maximum displacement, which is x. So I'm going to rearrange that equation for x. Halves cancel, divide both sides by k, take the square root, and plug in the values that you know. X final will become 0.6846 meters, and to 2 sig figs, that becomes 0.68. Please come see me if you have any questions.